Hello everyone, I'm Justin Millsap and I'm here with Harout, Matt, and Andre, and this is our final project for ARO-4090. The overall goal for this project was to determine the feasibility of utilizing magnetorquers for attitude control for a 3U CubeSat such that the z-axis of the spacecraft would be nadir pointing. Our Keplerian orbital parameters are that it is in a 500 kilometer circular orbit, has an inclination of 39 degrees, it has the right ascension of the ascending node of 90 degrees, and an argument of perigee of 0 degrees. Our actuators consist of 2 torque rod magnetorquers and 1 air coil magnetorquer, which their dipole moment is multiplied by A coefficients, and those coefficients would determine our feasibility for this project. The first part of our project was a magnetorquer analysis. We essentially simulated the magnetic field intensity that the spacecraft would feel in its low Earth orbit, and then we also calculated the control torques for the magnetorquers. Given its orbital parameters, we were able to find perifocal and ECI coordinates. Then from the ECI coordinates, we were then able to acquire latitude, longitude, and altitude. The first part of our Simulink model goes from perifocal to ECI, then to LLA coordinates, which is then plugged into the IGRF Simulink block model, which returns the magnetic field intensity in nanoteslas and the NED reference frame. Once a magnetic field was found, we could then calculate our control torque utilizing the equation on the bottom left-hand side. Here are the results of our magnetorquer analysis. On the left-hand plot, you can see that this is the intensity of the magnetic field, and on the right-hand plot, this is the magnitude of our control torque. This is all for one orbital period.
For the second part of this project, the azimuth angle and elevation of the spacecraft were determined throughout its orbit so that we could ensure a strong communication between the ground station and the spacecraft by accurately angling the antennas to their correct positions for effective communication. This was essentially done to enhance the efficiency of data collection, command transmission, and telemetry. To calculate the azimuth angle and elevation of the spacecraft, the Earth-centered inertial reference frame coordinates of the spacecraft were used as an input to the ECI position to AER block on Simulink, along with time as an input to calculate and plot the azimuth angle and elevation of the spacecraft. These are our results for the azimuth and elevation angles. The elevation angle indicates the CubeSat's height above the horizon. The bottom graph displays the azimuth angle, representing the CubeSat's direction relative to the ground station. We set a minimum elevation angle of 5 degrees, since below that angle the CubeSat would be considered too low on the horizon for effective communication. The contact time of the ground station, as indicated on the right here, is from 5:29 to 5:38 in Universal Time, or 9:29 to 9:38 a.m. in local Pacific Time. This time period of approximately 9 minutes represents the period when the CubeSat is within a favorable range for effective communication. Although this part of the project wasn't directly used for determining the feasibility of the use of magnetorquers for attitude control, specifically for nadir pointing spacecraft, it can be used for future projects that require effective communication and data transfer between the ground station at Cal Poly Pomona and the CubeSat.
Alright, so in part 3 of the project, we actually wanted to control the spacecraft, and so to do so, we needed to derive the equations of rotational motion incorporating control torque, disturbance torque, and gravity gradient torque. We did this for yaw, pitch, and roll, and once we did this, we inputted these equations into a MATLAB function block, where we took 2 derivatives of it to obtain the angular positions, and once we were here, we applied PID control to obtain control torques, and we compared these eventually with the available torques from the magnetorquers to see if the mission was feasible. So we're going to use those equations of motions and the angular rates to control the angle between V3 and V3. We want that angle to be less than 5 degrees because we want the spacecraft to be nadir pointing at all times, so we have better communication with the ground station. Here we start to derive the equations of motion, of rotational motion. Here we start with the basic rotational motion formula, incorporate the gravity gradient formula, and eventually solve for 0, so eventually we can isolate the double derivatives, which we will derive in a second. Alright, and here we have the conversion of RC, so pretty much the semi-major axis of the orbit, transformed into body fixed reference frame coordinates because they're currently in theta reference coordinates, so we use the rotation matrix RB theta to do so. Here we are deriving the angular velocity of V with respect to I in the body fixed reference frame coordinates. To do so, we use the principle of relative velocities. So we took the angular velocity of b with respect to theta in the body fixed reference frame coordinates, added the angular velocity of theta with respect to I in the body fixed reference frame coordinates, and we use PQ and R in the rotation matrix RB theta to calculate omega, or angular velocity of b with respect to I in the body fixed reference frame coordinates, as you can see on the bottom. However, since the angles are so small, we can apply a lot of simplifications. So we set the sine of the angle equal to just the sine, and the cosine of the angle equal to just 1, because the cosine of something near 0 is pretty close to 1, and the sine of a small angle is equal to just an angle. And so we multiplied some of these together, as you can see in the previous equations, and we realized that they're a lot, very less than 1, so we set them equal to the cosine of just the angles. We have a further derivation in the bottom right hand corner. We then apply further simplifications in the middle and the bottom, and we have our finished formula for the angular velocity of b with respect to I, the body fixed reference frame coordinates in the bottom left. Here we have further calculations for components in the rotational equations of motion. We need these to eventually solve for the double derivatives, so they are important to the process. Here we solve for the gravity gradient torque using all the angles. Eventually we are able to simplify it down to the orbital velocity, and we use the angles of phi and theta to compute the gravity gradient. So putting everything together, we have the finished derived formulas for the rotational equations of motion, incorporating the control torques and the disturbance torques. And we solve these for the double derivatives, which we input into the MATLAB function block, and we integrate it twice to obtain the angular rates. From here, we stem it out to 3 PID controllers, one for each of yaw, pitch, and roll, to obtain the control torques. So before we compare the magnetic field, or the control torques, and the available torques from the magnetorquers, we needed to convert the magnetic field vector into body fixed reference frame coordinates using all the rotation matrices on the right-hand side. And once we did so, we were able to compare the control torques with the available torques from the magnetorquers. We did this by using coefficients such as A1, A2, and A3, and testing to see if they were within a range of -1 to 1. If they were within this range, then the mission is indeed feasible, and that A value is proportional to the current flowing through the coil of the magnetorquer. And if it's greater than 1 or less than -1, then the mission is not feasible. Here we have the Euler angles compared with time. At the start, there is quite a bit of a disturbance due to the disturbance torque, but we will see that the control torque does cancel this out on the next slide. Here we have the control torque compared with time. As you can see, it does kind of correlate to the Euler angles. We needed to apply a torque to set those angles to 0, and you can see that at the very start. And then it eventually levels out because we don't need that much torque. And here we have those feasibility and A values that I mentioned earlier. As you can see, they all are within -1 and 1, indicating that the mission is indeed feasible using the magnetorquer torques. And as you can see on the right-hand side, the angle between B3 and V3, as I mentioned earlier, is less than -5 degrees at all times. So the mission was accomplished successfully.
Now let's wrap up this presentation by going over some conclusions and recommendations that we came up with. For the magnetorquer feasibility, we concluded that indeed the magnetorquers do generate enough control torque that's required to keep the satellite in a nadir pointing direction. For the controller, ultimately it was capable of maintaining the spacecraft nadir pointing. The requirement was for the alpha angle, which is the angle between the B3 and V3 direction, to be less than 5 degrees, but we were able to keep it to less than or equal to 2.5 degrees, so we exceeded the requirement there. Now for the feasibility of the project, we did the analysis for the coefficient of feasibility A and determined that it's going to be between -1 and 1, so therefore the project and the design is feasible. And for recommendations for future improvement, we could test out different magnitudes of disturbance torque to see if the control law is able to maintain the requirements, and just to simulate different disturbances that the satellite could see in orbit. And that's all for our ARO-4090 final project. Thank you.